Thanks for the invite. I thought it was a little, I didn't know what to talk about. You know, all we do is the gate model over there at Quantinuum. So, hopefully I put together some interesting stuff. It's great to be here. You heard Chris mention my name a few times. Chris and I worked here from 2007 to 2012. I got my PhD in 2012. You see, I'm work on the architecture, and you'll notice I use the same system as Chris. So I learned everything I know from him, I guess. Okay, so I'll go over the hardware a little bit, but I'll try to get to some of this other stuff too. So, you know, instead of using long chains, we use the so-called QCCD architecture. Chris is actually on the first paper that describes this concept. So instead of you know, putting all the ions in a single potential well, we use a bunch of little chains. So that's a cartoon of the creatively named H1 device, and it holds 20 qubits right now, and you'll see a bunch of 4-ion chains in there. So we do 2-qubit gates in those 4-ion chains, but there's a second species in there, barium-138, and we cool that ion, and then it sympathetically cools the data 170, the ytterbium-171 ion. And that's necessary in our system because we do a bunch of transport, and there's always a little bit of mechanical energy left over in the ions after we do a bunch of transport. And if you want a really high fidelity gate, you got to suck all that energy out. So let's see. So here's the new device. This is H2. It's currently populated with 56 qubits. And there's a bunch of benchmarks listed in that paper there. Okay, so to compute with this thing, you need linear transport, and then you need this swap primitive here so that you can pair any ion up with any other ion. So this is the CS department, or at least sponsored by it. So you've probably heard of bubble sort or parallel bubble sort. So this machine rearranges its ions using parallel bubble sort, and if you know anything about that sorting algorithm, you'll know it's like the worst sorting algorithm. You don't want to use it. And so we're trying to move past it. And to do that, we need to break out of one dimension. So we're going to go to 2 dimensions. So this is a real movie here. So this cartoon trap shows a 2-dimensional trap. You know, we're just showing 3 junctions here, but it has more. But this is the data I'm showing. And with this simple geometry, we should be able to rearrange ions much, much faster. So that's the future of our systems. I'm not going to talk a lot more about, you know, the size of the next system or how big we can go with this, but you know, stay tuned. That's where we're headed. Okay. So I think I already mentioned the top 2. So like I said, we have a lot in common with Chris's systems. We use the Mulmer-Sorensen gate to entangle pairs of ions. We're currently hitting 3 nines in the commercial systems. And then we have this mid-circuit measurement and feed-forward capability. We have pretty low crosstalk errors. I should have put the absolute error on the mid-circuit measurement. So if I go in to measure an ion, there's a 2e-3 error on that measurement result, and the rest of the ions in the traps get a 1e-5 error. And this is pretty simple for us because that QCCD architecture allows you to just peel off an ion and put it in some empty region of space where there's no other ions, and then you can hit it with a laser beam and not worry too much about infecting the other ions. Okay, so here's my first attempt to break away from the standard gate model. So we developed this gate. We call it partially entangling. There's a lot of different names for it. But anyways, the point is it's still a Mulmer-Sorensen gate. but you just turn the laser off kind of early. You still have to close the phase space loops and everything. But the nice thing about this gate for us is that the error decreases with the average rotation angle. So you should see that that point right there is about 1e minus 3, so that's a fully entangling gate. Then as you take it down to 0, the error decreases almost linearly. I say almost because there's an offset here. And that offset's super important for us. We concentrate on that offset quite a bit and try to minimize that thing. Just real quick, it's kind of an accident that this looks really linear. We have all sorts of errors in these gates, and they all have different functional forms. Like the spontaneous emission in this gate kind of scales like the square root of the time that the lasers are on, and then there's some coherent errors that scale quadratically. And then there's stuff that doesn't have any analytical form, like this phase noise from the laser. Your phase noise just has some structure. And but anyways, the point is when you average all these things together, you just happen to get something that looks like a straight line. It's just kind of an accident. Okay, so this isn't really beyond the gate model, but one of our favorite applications for this is characterization. So that we've heard a lot about this kind of stuff in the meeting. So, if you're using fully entangling gates and trying to synthesize a weakly entangling gate, then, when your simulation errors are dominated by the 2-qubit gate errors, and most machines out there are, and all 2-qubit gates are fully entangling, like I've depicted there, then better characterization actually adds more and more gate error. But if you go to this other, if you assume something like I just showed, where the gate error is linearly dependent on the rotation angle, and if there are no other errors in the system, then better characterization adds no error. Now that offset I was talking about earlier, it's pretty hard for us to squash that all the way to 0. If you think about it, there's probably some memory error associated with that, because remember we have to cool the ions before we do any gates. So we would have to have 0 memory error for that to go all the way to 0, but we can get it pretty small, we think. Okay, here's some recent data and theory to illustrate this a little bit more. So what this is the trace distance error in a quantum simulation circuit as a function of the size of the Trotter step. And these kinds of curves are very typical in real-world simulation experiments. So as you decrease the Trotter step error, or the Trotter step size, the simulation should get better and better. You had no noise or no error sources in the system. So you expect it to come down. But like we were talking about, you're adding more and more gates as you go this way. So eventually the gate noise turns this thing around. So that these are real data points from the machine, and then there's some theory curves here that show you what it should behave like. This one in particular is if there's no constant in that error model. So that's kind of where we're at now. I mean, stay tuned for us to show what kind of applications we can put this to use to. But this is a big focus for us right now. So this was our first attempt to show these partial entanglers are useful. This is data out of that review paper that I cited earlier. This is a quench simulation using this transverse field Ising model. And the whole point of this graph is if you use the fully entangling gates, you get the green data points. And if you use the parameterized angle gates, you get the orange data. And the blue curve is an exact simulation. So we were working in a regime, we only had 32 qubits at the time, so we could simulate this exactly. So the point is, the partially entangling gates work better. Now, like I said, stay tuned to see where we're pushing this, because the data should look a lot better than this when we report on it. Okay, and then the next and last ingredient I'll talk about from the hardware is adaptive circuits. So this is using mid-circuit measurement and then feeding forward to the rest of the qubits on the measurement results. a very well-known tool in the tool set. And this is, all this eye candy is just from a paper that my colleague Mike Fossfeig wrote to show, to prove that there's an advantage when you have these tools in your tool belt. And what he did was showed that you could prepare a state, a ground state of the toric code in a depth 4 circuit with fidelity higher than 50%, which is the limit if you only have unitary interactions. So, it kind of reminds me of like Bell's experiment or something. I mean, it's not as deep or anything like that, but it's just a proof of principle showing that you can create certain things in the lab with less resources if you have these mid-circuit measurement and feed-forward tools. Okay, so those are the tools, and then I'll talk a little bit about what we do with these things. Okay, so here's the first one. So this is Mike's work again. So this is outdated language. He used to call these holographic quantum algorithms. And the reason he called them that is because you can kind of reduce the dimensionality of the simulation. And what I mean is if we want to simulate a 1D quantum system, you can do it with a single qubit or maybe 2. And you can simulate an infinitely long 1D chain. If you want to simulate a 2D collection, you need a 1D chain of qubits. And the trick is to use matrix product states, but the quantum version of these things. So if you're familiar with these matrix product states, you've seen diagrams like this. This is a tensor network. It's just a 1D chain of them. And the trick is to map these isometries to unitary operations in the quantum computer. And if I translate this thing to a quantum circuit, I have one qubit running along the top, and then it's getting entangled with the first one, and then it's getting entangled with the second one, and then it's getting entangled with the third one. And the point is, this first qubit that it interacted with is done after that first gate. And so if you wanted to, if you have mid-circuit measurement and reset, you can measure that qubit right away after that first gate and then use it for the second qubit. And then as soon as that gate's done, you can measure it and reinsert it there. So that's how you get away with only one qubit, and you can simulate this infinite system. It's infinite in 1D. Okay, so here's just some quick data where we minimized this Heisenberg Hamiltonian and got pretty darn close to the ground state energy using only 2 qubits. So that's an infinite chain energy we simulated with only 2 qubits. So the point, what's going on here is, almost tripped, that these tensor networks, what they do is they change what resources are important. So usually we're used to thinking about classical simulations taking 2 to the n resources, where n's the number of qubits involved. But really the resource that's hard to capture is the entanglement in the system. Quantified by S, the entropy. So if you're exploiting a tensor network, the resources you need is only 2 to the S instead of 2 to the n. And in a lot of natural systems out there, the ground state is very weakly entangled. And so if you use classical tensor networks, as long as you're not right on a critical point or something like that, you can greatly simplify the calculation. Now in the quantum world, you can do the same thing, but we know we go from 2 to the n to n, in kind of brute force calculations, but in these quantum tensor networks, we go from 2 to the s to s. So it's kind of like you should put all your resources into the entanglement and not the qubits in the system. Okay, so, and then this is another demonstration that we did to kind of illustrate this point. So this is, again, looking at this transverse field Ising model, and we're looking for the critical point in the phase transition. And if we only have one qubit, we call these bond qubits, running through the system, then we get this, this data here. It gets pretty close to where the critical point is, but it misses it a little bit. if we just add one more qubit to this bond register, then we can kind of nail it. That's where it should be, and you see that data point right there. So this chi is the bond dimension if you know this language. Okay. These matrix product states are pretty limited in what they can do. They can kind of only effectively simulate 1D systems in a lot of ways. I mean, you can push them a little bit further, but they're not really designed to go much further. These, I guess the title's not up here, but these Mera ansatzes are much better at looking at critical phenomena where the entanglement is, approaching volume law or something. So Mera stands for what is it? Multi-scale entanglement renormalization ansatz, and it's designed to capture correlations between particles over an extended set of qubits. So you're just as entangled with your nearest neighbor as you are with a qubit across the room. You can build this tensor network, and that's what this is. I kind of love this picture. So what this is a 1D tensor network with periodic boundary conditions, and its time kind of goes out from the center to the edge. And you start in the middle, and you build up these correlations between these tensors, and then here at the end, we're going to measure the correlation function between this qubit and this qubit. And here's data over here, but if you look at this, you might be asking yourself, well, I thought you only had like 20 or 50 qubits, and there's a lot more in here. Okay, that's true, and what's going on is we're using that qubit reuse trick. So as we go out in the tensor network, as soon as a qubit gets out of the light cone of this correlation function that we want to measure ZZ between these two qubits. If there's a qubit in here that's not in that light cone, we measure it, we kind of trace over it, and then put it back into the calculation. So you can get away with simulating 128 sites with 20 qubits. And then this is the data showing what the correlation function should look like as a function of the distance between those two qubits. And we did have to use some error mitigation on this data, so I think the orange is, it's the raw. And there's two error mitigation techniques applied to this. One is checking the symmetry of the answer, and then the other is the zero noise extrapolation technique. And then you can see we kind of nail it. Okay. And then this is another one. This is looking at a non-equilibrium phase transition, or maybe a dynamical phase transition. So what this is, it's a quantum contact process. And what that means is, I think it's best to think of this thing as like a disease spreading model. This was a big hit during COVID. So what's going on is there's a couple of rules here. If you have two qubits next to each other and one of them is infected, there's some chance that it will infect its neighbor. And then there's another process going on where if you're infected, there's some chance that you'll just get better. There's some healing time. And so there's a competition between these two things. And it turns out that there's a critical value of P, such that the disease either doesn't spread. So what I'm showing here is like the yellow is some infected particle, and then time goes up. And if the probability to heal is really high, the disease won't spread. If the probability to heal is really low, the disease will spread. And then there's some critical point where it spreads like a power law. Okay, and so the way you implement this in a quantum circuit is with probabilistic resets. So that's the decay part. You probabilistically go from sick to okay. And then you do a bunch of C naughts with your neighbors in between. So that's the infection part. Okay, and finding this critical point is not trivial, but it becomes easier on the quantum computer. You just run this circuit. So this is the data, and you can see we're kind of hitting this, we're finding this power law behavior at the critical point. So you basically try to measure the slope of this line, which is the density as a function of time. And you can pull out the exponent on this line, and that tells you the critical behavior of this thing. You can see that the data kind of lifts off the line after a while, That's the noise accumulating. You eventually spoil the calculation. But we think this data is pretty old, and it's 2023 now. We think we've made some improvements. We can push this a lot farther now. So I really like this problem as for prospects for advantage, but the jury's still out, I'd say. Okay, so the next topic is like encoded computations. I thought this would be interesting for this crowd. So I'll introduce what is called the iceberg code. It's based off an error detecting code. So I think it's the most efficient you can get for qubits. You just need 2 extra qubits in the code, and then you get k plus 2, for k plus 2 physical qubits, you get k logical qubits. And the guys that did this work, they drew it like this, so that's why it's called the iceberg code. It kind of looks like an iceberg. These 2 top and bottom qubits kind of control the interaction between these logical qubits here. Okay, so how am I doing on time? 8 more minutes. Okay, good. So there's a lot of circuits that are fault tolerant in this code. You can do fault tolerant initialization, syndrome measurement. That all works perfectly fine. The really nice thing about this code is there's a really simple way to get a universal gate set. So a logical gate between 2 logical qubits maps to a single 2-qubit gate at the physical level. It doesn't get any easier than that, I don't think. So now, if you know about codes, your spider sense might be tingling because you're not supposed to be able to get like a universal set this easily. You usually got to do T-state injection or something like that. And the catch here is that this isn't a fault-tolerant gate. And if you think about it for a second, if I'm doing a gate like this, these are supposed to be error processes mapped out. So this should be like a 4x4 grid. These are different errors, like I get X on one qubit, or I get X on the other qubit, or I get XX errors or YY errors. These 3 errors right here are not fault tolerant, and that's kind of intuitive because they look just like the gate. So if I do a little bit too much of a ZZ rotation, there's no way I could tell that's an error because it just looks like a gate. And these ones are basically equivalent to that one up to single qubit unitaries. So those errors are undetectable in this code. But there's kind of a lucky accident for us. Now that this data is old, but what it's showing is cycle benchmarking data from our machine. And these are all the different Pali errors. And what you'll notice is the XX, YY, and ZZ errors are relatively small compared to the overall error. So those undetectable errors are a pretty small portion of the overall error budget. Okay, so just for completeness, I'll just describe this real quick. The blue is from the machine, and these multicolored bars are from simulations looking at all the different contributions from these different sources that we know about, and just using some modeling and then stacking them up. So, it's pretty good agreement, I'd say, between those. Okay. Okay, and the reason I'm talking about this is because this iceberg code has a neat property. So this is kind of a Rosetta Stone for this code. If you want a single qubit logical X gate, then you need to do a 2-qubit gate between that top qubit in the iceberg and some other qubit in the code. Okay, now the neat thing is these things. These products of X's or products of Z's or products of Y's. So if I do a circuit at the physical level that looks like this, it translates into something like this. And this gate is what I think is kind of interesting for this crowd. So, usually we're not used to being able to implement many-body gates like this. But this iceberg code makes it like absolutely trivial. Now, I asked this crowd, like, what do we use those for? So, I've come up with a couple of uses, but I would love it if other people dreamt up other uses for these things. So here's one that I came up with, or somebody else came up with. So this gate right here is common in like quantum chemistry simulations where you're trying to simulate fermions in the system. You're trying to do some gate like this. If you map those fermionic operators to qubit operators, you have to do this ladder of C naughts and then some variable angle gate at the end, and then you have to ladder back up, and then that implements this whole thing. So you can do that with a single gate in the iceberg code. So you cut out all those C naughts, which is a huge savings for quantum chemistry. Okay, and then here's the last idea I talked about. It's kind of similar in spirit. So this is new work. The author here, Henrik Dreyer, is leading this Quantinuum guy. So what he's trying to do is simulate fermions using qubits. And so he wants to simulate this Fermi-Hubbard Hamiltonian here. And the quote, standard solution to doing this, you first have to map these qubits to these fermions. And when you do that, you get these really high weight operators. So a really low weight operator for a fermion turns into this really long string of spin operators. Now this term turns out to be pretty easy, but this one's pretty ugly. Okay, and that really, really hampers these types of simulations. So the way around this, or one way around it, well, let me make one more comment. Like, if you think about this for a second, this almost kills the idea of doing fermion simulations with qubits without error correction, because if you scale the system up big enough, eventually this really high weight operator is going to get so noisy, it's just hopeless after a while. I mean, you could probably get pretty far, but there's no way you can claim that you can keep extending it to infinity. This error just keeps growing. Okay, so here's the trick. There's another way to encode these fermions using a so-called compact encoding. You have to look at these references here for theory details. But what you do is you put in another lattice in between the qubits that were already there, and that lattice is going to be prepared in a toric code state. And what that does is it stores the fermionic statistics locally, so that when you make this mapping and this encoding, you get these really low weight operators, and you can simulate these hopping terms with just a local spin operator. You see that ancilla? That's not a projector. It's called P because it's a poly operator, but it's just X or Y. Anyways, it becomes way easier, and now the error on that term there is not going to grow with the system size. Okay, so just to illustrate this a little more. So what's being illustrated here is, eventually you're going to simulate the system and you have to measure all these operators in there. And what's being plotted here is the error on an operator like this, where they're kind of right next to each other, even in the fermionic Jordan-Wigner encoding. You can see the error is pretty close to the noiseless value. This is, subtracting out the noise. But over here, you're looking at an operator that has this big long string. Okay, so you can see the slope on this data, and it's only going to get worse for larger and larger simulations. Okay, so we want to do this compact encoding. So remember, I have this auxiliary lattice sitting in here, and the trick is you use a coupling to this ancilla to hop between these 2 points. Now, that sounds kind of bad because you're going to end up with a 3-body term, and that's true. But so what this circuit diagram is supposed to show is if you write out all these 3-body terms and then just do kind of straightforward gate compilation, you can compile this way down, and it ends up not being very expensive to do this. I think I kind of already said this, I guess. So I didn't say this parenthetical. So the gate errors don't scale extensively with the problem size anymore. But since our system is not in 2D, it lives in this linear geometry, for us, the memory errors would scale extensively. So, we can't claim, oh yeah, we're done here. I mean, we'll have to build some 2D system like that matches this to really get to some, error rate that doesn't scale. But we can still run the algorithm and compare it with the Jordan-Wigner, so that's what this data is. So this is for a 4x4 system, and what he's doing is doing an adiabatic algorithm down to the ground state as a function of the number of trotter steps. So it's getting more and more trotterized as you go that way. So eventually you should get down to this ground state here. And so he's starting in a product state. It's not really that relevant. But anyways, so the blue is the Jordan-Wigner and the orange is the compact encoding. And they're basically the same for this 4x4 system. But remember, the Jordan-Wigner errors are going to scale with the size of the system. And that's what we see when we go to the 6x6. All of a sudden, the compact encoding is a little bit better. So, you probably like a little more separation between those two, but I think it's pretty promising. Okay. You can make some estimates for, when this encoding becomes, kind of hits the, am I done? Okay. I'll just stop. We think we can get away with pretty reasonable error rates and hit quantum advantage is the point. Okay. Yep, there's a couple positions open at Quantinuum if you're into quantum error correction. And if you want to access the machines, you can do it for free. Okay, that's it.
Thanks, David. Questions?
Thanks for the nice talk. So I want to ask about this quantum tensor network part.
Yeah.
So I guess this help a lot to reduce the experimental cost to do this kind of quantum simulation. But on the other side, this kind of tensor networks, they are often used for, classical simulating physics. And also, in this case, actually, the classical simulation also gets easier. You can even just simulate this single qubit with some measurement. You can do this. So I wonder, in the long run, do you expect this approach can do something that is, become classically really hard?
Yeah, it's a good question. So I think the point is, if you can take advantage of those tricks in classical, you better be taking advantage of them in quantum to make it as easy as possible, because these quantum computers are not easy to build. And the second part of that answer is, I'd say to make those simulations really hard, you don't just want to prepare a ground state, for example. You want to probably prepare a ground state and then put dynamics on top of it and do a quench or something like that, and then you'll be in business, or at least I think.
Thanks.
Yeah.
Any more questions? All right, since it's kind of late, let's thank David again.